So this is the 1 kilogram of a refrigerant. Okay. So 1 kilogram of a refrigerant. It starts out with a pressure of, so P1 is equal to 0.9 megapascals. So 0.9, if I put it in SI units, times 10 to the 6 pascals. A specific internal energy of 232.92. And this paddle wheel transfers energy to the system at 0.1 kilowatts. So if energy is being transferred through work to the system, is W dot positive or negative? Yeah, it's negative. So W dot is negative 0.1 times 10 to the third watts. And heat transfer occurs from the refrigerant at the rate kT, where in kilowatts, where K is a constant and T is time in minutes. So we'd like our time to be in seconds. So this is going to be, so let's say Q dot. And this heat is transferred out of the system, it says. So is Q dot going to be positive or negative? Wrong door. Yeah, so Q dot is going to be negative. We'd like the units to be watts, so it's going to be 1,000 K, but the time is in minutes. We want the time to be in seconds. So we need to divide by 60. So what's 1,000 divided by 60? I think 16.6.
Yeah, 16.6.
Okay, 16.6. Okay, and then what do we know about state 2?
Since it's a closed system, the pressures don't even matter, correct?
The only way the pressures, right, I don't really see how the pressure is going to come into it right now. Like normally, yeah, sometimes I'm using some of these problems from textbooks, and in this class particularly, they throw a lot of unnecessary facts in there because the whole game is trying to figure out what you want and what equations are going to get you there. And so, all right, so state 2, we got P2 of 1.2 times 10 to the 6 pascals. U2 is in, that was also in kilojoules. So I'm going to write this in joules per kilogram. And at state 2, it's 276.67 times 10 to the 3 joules per kilogram. No change in kinetic or potential. The first part is just coming up with, and we're supposed to do 20 minutes. Okay, 20 minutes. What's 20 times 60 is 1200. Okay, so time is equal to 1200 seconds. It's 1 kilogram of gas. So to go from the specific internal energy to the extrinsic internal energy, you just multiply by 1 kilogram, so you get the same thing here. So let's write out the equation. So we know that let's write out the full form. And this is the differential one. So dE dt is equal to Q dot minus W dot. It says don't worry about kinetic and potential, so du dt is equal to Q dot minus W dot. And since we're given a finite amount of time, we're going to solve this differential equation, integrate this. So you can think of it like this. Du is equal to Q dot minus W dot dt, and then integrate those from state 1 to state 2 in both cases. If you integrate du from state 1 to state 2, you just get 270. You get the later state, the internal energy at state 2, minus the internal energy at state 1. Is equal to the integrals of these two things. What? So Q dot, so we got the integral from state 1 to state 2 of negative 16.6 repeating minus negative W. I didn't complete this thing. So what we have is negative 16.6 repeating times t, where this is in seconds. And the rate of work is, okay, so I got to put this t in here, and then minus a negative 0.1 times 10 to the 3 dt. So if you do this subtraction, what do you get there? 43 point.
Oh, sorry. 43.7.
87? Okay, times 10 to the third is equal to, and we're integrating this side with respect to time. And so we have to, so our boundaries are going to be the starting time and the ending time. I'm just going to think of that as from time 0 to time t, okay? Well, actually, we don't need to use time t. We know that we're given that it's 20 minutes, which is 1200 seconds. Negative 16.6 repeating t plus 0.1 times 10 to the 3 dt. Yes. Thank you. Anybody still with me on this?
The most.
Okay. I just, the two things I did was I was so excited to calculate 16.6 repeating that I forgot all the rest of the stuff in this expression. So here's what it should look like. Okay. Now we put it into the equation. Now we're integrating this with respect to time. So we have 43.87 times 10 to the third. If you integrate this with respect to time, you get minus 8.3 repeating times k times t squared plus 0.1 times 10 to the third times t. And this is evaluated from t equals 0 to 1200. And so 43.87 times 10 to the 3. 1200 squared times negative 8.3. What do you get there? And this is an equal, not a plus.
.2 E7.
Okay, and we still have that k, and then 1200, so plus 120 times 10 to the 3. Okay, and so it looks like, now you can solve that. That k is going to come out negative, but subtract 120 times 10 to the 3 from both sides. What do you get over on the left side?
Negative 76.13.
Is equal to 1.2 times 10 to the 7 k. And so what do you get for k?
Negative 6.34.
Negative 6?
Yeah.
And whatever units go with that.
So on your example, I think you got something different.
Oh,
So that's why I was confused. I did.
I'm not surprised.
Well,
It has too many steps for me to.
well,
The difference in what threw me off was when you switched to seconds.
Uh-huh.
We didn't multiply by the 1,000 in the example.
Oh.
The
Yeah.
answers.
Okay.
So I'm sitting there trying to figure out
Yeah.
units and everything. So.
Okay.
because I did everything. I did the equals separately.
Uh-huh.
I didn't don't together, whatever.
Yeah.
And I think your answer is actually what Q is equal to Q.
Oh.
So I don't know.
Uh-huh.
I don't know. So I was confused. Like.
Okay. Yeah, sorry about that. So number 4, it sounds like I should look back at that. Anyways, I'm not confident in the answer I got here, but that's how you do it anyways. Maybe there's a
I think I got the
arithmetic
same-
mistake
I worked
somewhere.
here and got the same answers.
Okay. Any other homework questions you'd like me to go through? Okay. Okay, so the next thing we're going to talk about is simple compressible substances, which basically what we know about the kind of materials that we're going to be dealing with in this class always. So simple compressible substances. And this is going to, this is every material that we're going to deal with in this class. And in order to be a simple compressible substance, there are two requirements. The first is that it's homogeneous. That just means that it's the same everywhere. You can't have clumps of stuff in it, you know. A chocolate chip cookie is not homogeneous, but a sugar cookie is, kind of thing. And second, it can't have any, it doesn't react to magnetic or electric fields.
Are there gases that react to electromagnetic fields?
Apparently, but I don't know what they are. I mean, I guess, yeah, if you have, I mean, if you have a beam of electrons or something, you know, like you do labs like that in physics too, you know, that could be your system, you know, but it reacts to electric fields. So like you can't expect it to behave according to these laws. Okay, for any simple compressible substance, so this is really, I mean, kind of a foundational fact for simple compressible substances. For any simple compressible substance, if it's not at a phase change boundary, if you know any two properties, that's enough to specify the entire state. Okay, so if you have water and it's not at a boiling point, freezing point kind of thing, and you know the pressure and the temperature, that's enough to determine the specific volume, that's enough to determine the specific entropy, enthalpy, all these other properties. Okay, so two properties is all you need. It's even better if it is at a phase change. So if it is at a phase change boundary, then you only need one property to specify the whole state. Being at a phase change boundary is what we're going to call saturation. So then any one property specifies the entire state. Okay, so this makes sense if you think about water. Like if you say, okay, this water is at the boiling point, maybe some of it is steam, some of it is liquid. What's the temperature? You know? Well, that's not enough information. But if you specify the pressure, then it's like, oh, well, I know that at this pressure, the boiling point is this. So if you specify one property, you can figure out anything else from that. Okay. What about just water sitting there, liquid water? You're like, what's the temperature of that? Like, who knows, you know? So in order to do that, you have to say, well, the pressure is this, and it has this much internal energy, specific internal energy or something. And then from that, you can say, okay, yeah, the temperature then is 47 degrees. Okay. So think about water and those make sense. But the key thing that we're going to use over and over again is if it's not changing phase, you need two properties. If it is changing phase, you need one property. The relationship or relationships between pressure, specific volume, and temperature can be shown in a PVT surface. So let me show you what those look like. And you'll agree that it holds a lot of information in it, but it's a little hard to interpret. And so we're going to often use projections of this 3D thing. But I want to insert a picture. So here's a PVT surface. Can you see that okay? It's not the clearest picture, but that three-dimensional shape, you know, it's only a surface, it's not a solid. But if you choose a volume and a temperature, you know, plot some point in there, that specifies what the pressure is. Okay. Some things that you can see here. Notice that something happens. Okay, so let's get our bearings a little bit. If you're over here on the surface, it's a liquid. Okay. If you're over here on the surface, inside this thing that we're going to call the vapor dome, it's going to be an important feature all the time. It's a mixture of liquid and vapor, liquid and gas. So this is during the phase change. Okay. Over here is gas. Above here is a critical state where you can't distinguish between liquid and gas. We're not going to deal with that too much until later. And then over here is solid. In this class, that's not going to be very important to us because, and I'll talk about why, but this phase change between liquid and gas is a super valuable range of properties for power cycles, refrigeration cycles. Okay, we'll talk about why that is. Notice this thing that happens. So this axis is volume. Okay, notice what happens when you go from the phase change from liquid to solid in this surface. Okay, you can see that the volume suddenly decreases. Okay, so this is for a material that contracts on freezing, which is almost everything. There's one material that expands on freezing. What's that? Water. There probably are others, but it's very rare, you know. So this is the PVT surface for something other than water, where the
Water is polar.
I don't know why it is, but I know that it's like very lucky that it works that way because otherwise lakes would freeze solid in the winter and that would be very bad for frogs and fish. Okay, draw. So this is the key thing. You can see that on freezing, the volume reduces. So this is not water. For water, hold on. You get something like this, and you can see that it goes the opposite way at that freezing point. The volume increases suddenly. And so that is the PVT surface for water.
So if water didn't do that, lakes would freeze solid.
Yeah, so what happens is, the coldest area in the water freezes. And so once it's frozen, it becomes less dense, which means it floats to the top and keeps the warmer stuff down below, If it got denser, it would sink and it would just freeze from the bottom up, yeah.
Yeah, ice fishing would be very fun.
Yeah, exactly. It'd be a lot of drilling and not much fishing. Okay, so this is for a material that expands on freezing.
Didn't even think about that.
So this is water. We are not going to use that surface because it's pretty inconvenient trying to read values off a 3D plot. So we're going to look at basically projections of this. I think I have one here. Okay, so you can see there's the PVT surface in the middle, and you can do projections in either direction. You can also, this PVT surface, remember, any two of those axes you specify is enough to specify any property, not just the other one that's on this graph, but it's enough to specify specific entropy, specific enthalpy. And so you can do projections of all these things, even using variables that aren't on this 3D plot. You can do temperature, entropy, all these things. The most important feature for us in thermodynamics is the vapor dome, which is a really sweet name. Mad Max Beyond the Vapor Dome. And it comes up, you'll see this vapor dome in a lot of these projections, but it always is something like this. And on this side, the material is a compressed liquid, it's called. That just means it's a liquid. Inside here is a liquid vapor mixture. and on this side is a vapor. When you get above, this is, I'm thinking of a projection on a pressure and temperature graph. When you get to this temperature and pressure, that's called the critical point. Above this temperature and pressure is what's called a supercritical fluid. You lose all distinction between liquid and gas. And then the last important feature of this vapor dome is this green line here is the triple line. That's where solid, liquid, and gas can exist in equilibrium. Let me give a couple of definitions. So, compressed liquid that's a liquid that's not at a phase change boundary. A saturated liquid is a liquid at the phase change boundary. And what that means is adding energy to a saturated liquid turns it into a vapor. Whereas if you add energy to a compressed liquid, you just raise the temperature of the liquid. Okay, so this is an important instant, sort of. So saturated liquid, it's still all liquid, but all of it's ready to change.
So
Okay.
by saturated, it's like saturated with as much energy.
I guess you can think of it that way. That makes sense to me, yeah.
And then it kind of hangs right there at that same temperature.
At that temperature, yeah, we'll talk about that. And that's going to be like really a key to being able to do refrigeration and power cycles and stuff like that. It's a really useful thing for engineers. A saturated vapor. Well, what would you guess a saturated vapor is? Yep, so that's vapor at phase change boundary. Removing energy changes it to a liquid. Okay, so if you look at the vapor dome, here, it's a vapor, you remove energy, it gets to this boundary. It's still, if it's on this side of the vapor dome, it's still all vapor, but if you remove any more energy from it, you start to get a mixture of liquid and vapor until you remove so much energy that it's all a liquid on this phase change boundary. then if you keep removing energy, it starts to be a liquid. There's stuff like this, interesting stuff like this, a lot we could say about the phase change boundary between liquid and solid. It just isn't as useful to engineers, so we're not really talking about it.
So that dome, it's kind of a flat surface on the temperature.
Well, you can tell from here, it's sort of, yeah. And then the last definition, so that's saturated vapor, saturated liquid. Once you get away from the phase change boundary for a vapor, it's called a superheated vapor. So vapor not at the phase change boundary. Anybody have any questions about any of this yet?
So I'm thinking back to chemistry class.
Yeah.
And you've got your little graph where you have energy temperature going up and you get your phase change flat.
Right. Yep.
That is the vapor dome.
Yeah, so I'm just about to show that on a temperature volume graph. So phase change. And again, we're just concerned with the liquid vapor phase change. So put temperature on the vertical axis, volume on the horizontal axis. There's the vapor dome. And for a constant pressure, what you get is something like this. As you add energy, you mostly get a change in temperature for the liquid. Okay, this is liquid over here. This is a liquid vapor mixture. This is vapor. Once you get to the vapor dome, once you get to saturated liquid, adding more energy now doesn't change the temperature anymore. The temperature stays exactly the same. And that liquid just changes little by little until it's all vapor. Then at that point, the temperature will start to go up again like that. This red line is represents a constant pressure. So what happens to the phase change boundaries as you increase the pressure? If the pressure increases, it's harder to boil water. And so you'd get something like, if you had a higher pressure, it would look something like this. That's if you increase the pressure. And for a lower pressure, you'd get something like this.
Or we just,
For mountain climbers, boiling their food when they get up close to the top of really high mountains in the Himalayas and stuff becomes a problem because the boiling temperature is so low that like you can't cook your rice or whatever, you know. It's like you're trying to cook something at 75 degrees or whatever, you know. It takes forever apparently. And it's because of that effect.
That'd bring you to some problems.
Yeah, exactly. That's a lot to carry, but maybe that's a good idea. So, okay, so why is the vapor dome useful for engineering? And actually, there was one other thing I wanted to say there. Okay, hold on. That the energy difference between the saturated liquid that's the lower energy, and the saturated vapor, that's the higher energy, is called the latent heat. Okay, the best explanation I can think of for why they would call it latent heat is you can think of it's sort of hidden energy that doesn't show up in the temperature but is present in a vapor. Okay. So it's energy held by a vapor that doesn't show up in the temperature, that isn't shown by the temperature. Okay, so now why is the liquid vapor phase change important in engineering? The reason is you're often trying to use temperature differences to move energy around. Okay. So let's think of a case where you have a superheated vapor that's at, let's say this is at 75 degrees. Okay. And you have surroundings that are at 80 degrees Celsius. Okay. How much energy can you put, how much energy can that temperature difference transfer from the surroundings to the vapor? So transfer from the surroundings to that vapor. And the answer is not that much because all the energy that goes from the surroundings into this superheated vapor is going to raise its temperature. Okay. And as its temperature changes, it gets closer to the surroundings. And once it gets to 80, there's no more energy exchange. So the vapor temperature rises, reaches 80 degrees, and then there's no more transfer. But now think of a case where instead of having a superheated vapor at 75 degrees, you have a saturated liquid at 75 degrees. And the surroundings are 80 degrees Celsius. Well, in this case, without the temperatures getting any closer together, you can put in that entire amount of latent heat, okay? So a lot of energy can transfer here before the temperature changes. You know, before the vapor temperature rises. The amount you can put in is the entire latent heat. And there's also latent heat between a solid and a liquid, but it's tiny compared to the latent heat between a vapor and a liquid and a vapor, okay? It's a ton of energy that you have to put into a liquid to turn it into a gas. It's a relatively very small amount of energy you have to put into a solid to make it a liquid. Okay, and the latent heat from liquid to vapor is very big. Okay, so that's basically the idea of why refrigeration compressors and all this stuff is designed to work right at that phase change temperature, because there's a huge amount of energy available to change location without big differences in temperature. Okay. Okay, well, what we're going to get into next time is property tables. And property tables, you don't really use physical tables anymore. You use programs, but we don't have those programs, so we're going to use these tables. It's not a big deal. But these property tables will let you look up, okay, so if I have a compressed liquid and I know the temperature is this and the pressure is this, I can look up all the other properties, enthalpy, entropy, whatever. At a saturation point, remember, you only need to specify temperature or pressure. You only need to specify one thing in order to find all the other properties. So we're going to use that fact with these tables so that we can look up for a certain material, certain refrigerant or whatever. Okay, here we know the internal energy is this. What's the temperature going to be? That kind of thing. Okay, so that's what we'll do next time. Anybody have any questions?